to drive into the base of inverter amplifier Q32115, which drives the current amplifier, which in turn drives the series regulator. Now remember, this supply provides 500 mils. The overload protection sensing resistor is our 32139. Now we're back to a single overload transistor, Q32137. The foldback divider, R32137 and R32138. Now Q32137 is off during normal operation. However, if you increase the load requirement to greater voltage drop across R32139, that'll then drop the emitter of Q32137, turns that transistor on. It pulls some current from R32110, reducing the current through Q32115. That reduced current biases Q32143 to less conduction, which in turn begins to shut down the series regulator Q32139. Now back at the minus 50 volt comparator, the diode CR32130 protects the base emitter junction of the A side of that comparator in case we lose the minus 50 volt supply. In that case, you see Q32130B base would go to ground, and the base of the A side would go to a minus 9 volts, having been pulled down by the start circuit. Under that condition, CR32130 comes into conduction. Now, CR32128 seems to be redundant. It would protect the base emitter junction of the A side of that comparator transistor in the same manner. The diode appears to have been left over from an earlier design. Now, a point that I should have made earlier is that triangular-shaped ground, which appears by all of the error comparators. Now, that is a ground sense, or a sense ground, and it's taken from the motherboard over in the same area where the sense voltages come from. Now, I said earlier that we wouldn't discuss the readout on this tape. However, there are some differences between this instrument and the 7704 not A that we should mention. Now, most of these differences have to do with the processor. So if we turn to pull-out schematic 10, the readout system, and just leave that one folded in the book, and then pull out schematic 11, which is labeled main interconnect. Now, that's a connection between the acquisition unit and the display unit. Then if a processor is used, then the communication with the processor would be through these same plugs and connections. Now, the first change that we'll talk about is the writing of decimals. You recall that the readout system was capable of writing 5 decimals out of the available 10 time slots. Well, if we're going to communicate with a computer or with the 7M13, which has a keyboard on the front of it, then it's necessary to place decimals wherever you want them in any of the 10 time slots, and not crowded between 2 characters, but rather occupy a space all of its own. Now, you may want to turn to the character selection matrix. That's on page 2-41 in your manual. And there under row 8, column 9, you might place a decimal. That's the character decimal that we're going to use in this instrument. All right, back to schematic 10. We pick up row 8, right square in the middle of the page, out of U3429. Pin 3 down below is row 8. Now, that's not used in the previous 7000 series instruments. And that row 8 goes off to the right. I guess a good place to find it would be the format generator, U3480. Start top left of that IC, pin 7 off to the left, R3479, tied to row 8. Now, that resistor was added. Now, that provides the Y information to the format generator for writing the decimal character. Now just to the right of that resistor, a little above, is R3478, also connected to row 8. And you'll notice that goes to pin 2 of the format generator IC and provides the X information for writing this decimal character. Now, just below there, U3470 has R3474 tied to a minus 15 volts. You might check your manual there. Mine says row 8, that should be minus 15 volts. Now that alters that IC so it allows one to write that decimal character. Now that's all there is to the modification, and it is a field mod, by the way, to older instruments, which will allow those older instruments to be used with the 7M13. Now the 7704A has the row and column data switches on the acquisition unit rather than up there by the rest of the readout. The reason for that is that we need to be able to feed row and column current information into the processor, and in turn the processor needs to feed row and column data information into the display unit. So if you look at the row and column data switches, you notice that the current output there at pin 7 go into grounded base amplifiers Q2070 and down below Q2030. Now that is a current in 100 microamp increments, you recall. That feeds over to the display unit, where it passes through an equivalent of about 5.5 K. Then we pick off the row match adjustment. Now that's new with this instrument. Now theoretically that would be 500 millivolts per step in at pin 10 of U3429, for example, the row decoder. However, there are differences in ICs, different requirements, and that's the idea of this adjustment. Now the 500 millivolts plus per increment, as it appears at J2002, is read by the processor. Then when the processor wants to talk to this display unit, it feeds 100 microamps per increment in at J3402. Now during the time that the plug-ins are driving the display unit, when the bases of Q2007 and Q2030 are pulled high through CR2051 and R2053 toward 5 volts. Now the anode of CR2051 is tied to the processor, and when it wants to drive the display unit and shut off the plug-in drive, then that point is pulled down to ground, which turns off Q2070 and Q2030, allowing the processor to drive the display unit readout. Now the shielded cable that goes into J3402 with the row current picks up a signal on the shield, and the shield is connected to the top of that divider composed of R3420, R3422, and so on, thereby that row match adjustment, such that that's a differential signal applied. Now the shield is also connected to pin 7 of U3429. Notice that little lopsided cross or whatever it is there to indicate that those points are all tied together. It's got 15 volts on it, all right, but it also has some signal current. Then down below where the column current goes into J3401, we have the same deal there, only this is a different shield and a different set of signal currents, indicated this time by an asterisk, and that point is tied to the top of the column match divider and also in at pin 7 of the column decoder U3418. Now another difference is the channel counter. It's now U3450, a single IC, rather than 3 separate ICs as in the older instruments. Its output then feeds not only the row data switch and the column data switch, but also the processor. The processor in turn can provide its own channel address information. Now the channel addressing sequence has been changed, and you'll find that on page 2-48 in your manual, table 2-3, where we address channel 2 left, then channel 1 left, channel 2 right, then channel 1 right, and so on. Instead of in the older instruments, we addressed channel 1 left, then channel 2 left, and so on. Now another change is up in the upper left-hand corner of things, where the end of frame pulse goes into a edge shaper circuit. Now we'll use the end of frame pulse, the negative excursion, in the gated readout mode of operation, and perhaps we should review that. Now pin 2 of the timer IC, U3433, will be low when we're in free run operation. In free run operation, pin 8 of the flip-flop U3449C and D will be held high by the pull-up through our 3449. Now that supplies a low at pin 10 of that NOR gate, and that low in at pin 2 of the timer places the readout in free run. Now you may want to pencil in the conditions in that flip-flop composed of the two NOR gates. Pin 8, as we said, is high. Drop down, and we can see that pin 11 is low. It's tied directly to pin 10. And pin 12 is low. Now we said we were going to utilize the negative excursion of the end of frame pulse, and that hasn't arrived yet. So we have a high at pin 2 of U3449A, a low at pin 1, a low at pin 12. Okay, with the low at pin 11 and 12, then we have a high at pin 13, a high over at pin 9. Okay, a high at pin 8, a high at pin 9, a low at pin 11, a low at pin 12. Now just as soon as the readout mode switch on the output signals board is thrown to gated mode, pin 8 goes low. But you see, with the high still at pin 9 of the NOR gate, it doesn't change the output there at pin 10. Nothing happens. Now at the end of frame, after all the characters have been written, then pin 2 of U3449A goes low. Now notice the inverter U3449B. Now there's about 100 nanosecond propagation time through that inverter amplifier, so that when at the end of frame pin 2 goes low, pin 3 doesn't go high for 100 nanoseconds. In the meantime, with both pin 2 low and pin 3 low, we get a high at pin 1. Okay, that narrow pulse then goes in at pin 12 of U3449D and switches that flip-flop. Pin 10 goes high. That high in at pin 2 of the timer IC locks out the readout. At the end of sweep, a positive going pulse of rather short duration comes in at pin 8 of the flip-flop, switches it again. Pin 10 goes low. The low in at pin 2 of the timer IC switches to free run operation. It free runs then for a complete frame, and then at the end of frame locks out again by switching the flip-flop and placing pin 2 of the timer IC high. Let's look at pull-out schematic 11. There we have two rows of plugs. Now mostly they're P20 front and rear. The center of the page represents the acquisition unit, and the two outer edges, the display unit, Let's start at the upper left-hand corner. Now the following connections interface also with the processor. First, the push-pull vertical signal, then pin 27. Pin 26 is that 15-volt shield we talked about. Pin 19, 18, 17, 16, 15, 14. Drop down to pin 5, 2, 1, and then the push-pull horizontal. Up the upper right-hand corner, the Z-axis signal. Pin 27, which is the interface ground. Pin 26, pin 25, and clear down at the bottom, pin 2. Now the other connections just go between the acquisition unit and the display unit, but not to the processor. The inverter power supply and the rectifiers are found on pull-out schematic 8. Now right in the upper center, Q3034 and Q3047 form an oscillator which runs at 25 kilohertz or so. The output from that oscillator drives transformer T3101, and the rectifiers in the secondary provide what we will term the pre-regulated supplies. Now they'll all be regulated again, with the exception of the 5-volt supply. Now the 54-volt, when regulated, becomes the 50-volt supply. The minus 54 becomes the minus 50-volt supply. The 17, the plus and minus 15-volt supply. The plus 7 becomes the 5-volt regulated supply. And the plus 5 down below that says lights is not re-regulated, and it supplies the front panel lights. The lower center of the diagram, U3105, is a Tech-made inverter control IC, which controls the frequency of the oscillator up above, and thus the pre-regulated supply output. Well, let's begin in the lower left margin with the power plug. We go through a line filter. It's a single package. Through a 4 amp line fuse. Both sides of the line is broken by the power on switch. Then next comes a filter composed of our R3005 and C3005 and C3006. Now that suppresses silicon spikes. We're talking about the surges of current when the silicon rectifiers fire. Then we see the line selector switch in the 115 volt position. Then we use the 2 right-hand diodes in that bridge as a voltage doubler. When we're in the 230 volt position, the bridge is used as a bridge. In either case, the DC output will range from 220 volts to 360 volts, depending on line voltage. DS3008 and DS3013 up above are protective devices. They're rated at 230 volts, plus or minus 15%. Now, when that voltage is exceeded by a line surge or plugging the instrument into too high a line voltage, then the device will short and blow the fuse, thereby protecting the rest of the circuits. In the 115 volt position of the line selector switch, DS3008 is in the circuit. In the 230 volt position, both of them appear in series. Now that 230 volt rating may seem a little high, but remember that's peak-to-peak value or surge value, where the 115 and 230 volt at the input is an RMS value. Now the filter capacitors, C3016 and C3017, which are used as part of the voltage doubler and as straight filters in the 230 volt position of the selector switch, are in series. They're only rated at about
200 volts apiece, so it's important that they both charge at about the same time. Well, off to the left of the rectifiers there are 3013 and our 3008 effectively appear across those capacitors to assure us that they charge at about the same rate. In series with our 3008 is T3001. Now that transformer provides the line filter and also a line into the inverter control IC is called line sense. It senses whether the line voltage is present or not, and we're going to use that to shut down the inverter as soon as the power is turned off. Now at that time, if the inverter is shut down, then the only bleeder for the filter capacitors is our 3021. Now that takes some time then to discharge those filters, so there are lethal voltages present even after the power switch is turned off. So a relaxation oscillator is formed of our 3019, C3019, and DS3019 that continues to blink until that voltage gets down to about 70 volts. Now, effectively in series with the filters is thermistor RT3009. Now, an initial turn on, that resistance is high enough to limit the current as we initially charge the filter capacitors. Now, when you turn the instrument off, the discharge time of the filter capacitors through our 3021 is matched to the thermal time constant of RT3009, such that by the time that the filter capacitors have discharged, the thermistor will have returned to its cold condition so that it can limit the current into the capacitors the next time the instrument is turned on. Okay, there's a 2 amp fuse to protect the DC circuits. T3025 rejects common mode current surges. R3025 just damps that inductor. Now the current spikes that can't get through the inductor pass to ground through C3027. Now that's reference ground rather than chassis ground. Following that is a filter composed of inductor L3029 and capacitor C3029. Now that circuit isolates the current surges, and hopefully only sine waves of current are drawn from the input filters and returned to the input filters. Because yes, this high efficiency supply does return current to the input circuit. Well, let's take a look at the oscillator. Q3034 and Q3047 are in series. That is, the emitter of Q3034 is tied to the collector of Q3047. The collector of Q3034 is tied to the positive end of the rectified supply. Now, as we said earlier, that can swing all the way from 220 volts to about 360, depending on line voltage. But let's call that 330 volts now. That's a nominal value. So when Q3034 is on and saturated, the emitter of that transistor and the collector, Q3047, is pulled up to 330 volts. Now the emitter of Q3047 is tied to the minus side of the supply, the DC reference as we'll call it. So when Q3047 is on and saturated and Q3034 is off, then that common tie between the emitter of the top transistor and the collector of the bottom one there is down at 0 volts relative to the reference of this supply. So the emitter of Q3034 will swing as a square wave between 0 volts and 330 volts. Now that square wave appears across a series circuit composed of first L3037
and C3037. Now that's a series resonant circuit, resonant at 28.9 kilohertz. Next in series is the primary of transformer T3001, then the primary of T3035, and then the one-turn primary of T3030. Now this oscillator is free running. We're going to slow it down a little bit to provide regulation, but it requires a start circuit in order to get it going in the first place. All right, the start circuit consists of the 4-layer diode CR3040, capacitor C3048, and then to the right and up, diode CR3046. Now you turn power on, positive half cycles of rectified voltage appear at the right of thermistor RT3009. Remember we discussed that earlier. Now there's a divider composed of R3010 and off to the right R3048. Now those positive half cycles begin to charge C3048, plus on the bottom, minus on the top. As that capacitor begins to take on a charge, it pulls up on the anode of CR3046, providing a collector supply for Q3047, and beginning to charge C3037. Now that's the capacitor over there in that series resonant circuit, remember? Now back to C3048. As soon as the charge has reached 32 volts, CR3040 fires. I know that's a term that we've used with neons, but it seems appropriate here. Anyway, the voltage drop across it reduces to just a few volts. Now we have a positive step, therefore, at TP3040. That positive step goes up, couples through C3042, lifts the base of Q3047, turns that transistor on. Now current begins to flow in through that transistor, through the series resonant circuit, through the primary of T3101, over to the left through the primary of T3030, in such a direction as to induce a current into the base of Q3047. Now it's regenerative, and Q3047 draws even more current. Now because L3037 and C3037 are resonant, we'll have a sine wave of current flowing. So if you'll just sketch briefly that sine wave of current, we begin with the current increasing. As soon as it reaches its peak, it begins to decline. We're now into the second quadrant of that sine wave. Now as you look at the sketch of the sine wave, you'll notice that the point of greatest rate of change occurs at zero crossing. Now we'll take that fast rate of change and differentiate it. Now we pick it off of transformer T3035, feed it down and through a differentiating network composed of C3125, C3126, and some 2K resistors which are inside of the IC there at pins 10 and 11 of U3105. There are also diodes to ground from pins 10 and 11 inside of the IC, such that we'll utilize only the positive excursion of that differentiated pulse at the time of zero crossing. Now, since we're taking a waveform from both sides of the secondary of T3035, we get a positive going pulse into the IC during both the positive going zero crossing and the negative going zero crossing. All right, that pulse goes into the IC. It switches a latch, which in turn places a high at pin 9 of the IC. That turns on Q3102. The transistor saturates. As its collector pulls down to ground, it pulls down through CR3101, CR3102,
placing a short on the secondary of the transformer T3030, there at those two 30-turn windings. All of the current in that transformer, therefore, flows to ground. No current flowing into the base of Q3047. That transistor turns off. Now consult your sketch of the sine wave of current. This all occurs at zero crossing. Now, since this is zero crossing, that means that the current direction has reversed. Now, with Q3047 turned off and Q3034 turned off,